Good morning, I'm Konstantin and I'm going to talk about algorithmic chip talk. This is a joint talk with Yakov Babichenko, Inbal Talgam-Cohen, and Haifeng. We'll start with a short introduction, then we'll see the formal mathematical model of chip talk. Later, we'll see both positive and negative computational results. And finally, we'll make some points for future research. So first of all, let's talk in general about information design. Many real-life situations involve strategic revelation of information. And more specifically, a certain sender who is well-informed tries to persuade a less informed receiver to act in a certain way. For example, it can be a journalist trying to persuade her reader or a politician trying to persuade voters. And it even happens in some social games such as Mafia. We capture the information available to the sender, but not to the receiver by a certain abstract state. For example, in the game of Mafia, the state is the role of a certain player in the game, because this role is known to this specific player, but not to the other players. And it's common to assume that the state is drawn from some common knowledge prior distribution. There is a celebrated model on strategic revelation of information called Bayesian persuasion, which we're not going to talk about today. This model was introduced by Kameniec and Gensko in 2011, and it makes quite a strong assumption that the sender has commitment power, meaning that the sender can transversely commit to some randomized revelation policy of the information. But this assumption is unrealistic in some cases. For example, in social games such as Mafia, why should we believe that some player can transversely commit to an information revelation policy? So we're going to talk about the more basic model called chip talk. It was introduced by Crawford and Sobel in 1982. And this model assumes no special powers from the sender side. But unfortunately, this model is harder to analyze compared to Bayesian persuasion. In the chip talk game, the sender strategy is a randomized mapping from the states to a certain set of signals, while the receiver strategy would be a randomized mapping from the signals to the possible actions that the receiver can take. Despite the practical importance of chip talk, it has not been systematically studied from computational point of view before our paper. So this is what we do in our paper. We focus on computational aspects of chip talk, mainly from the sender's perspective, similarly to Bayesian persuasion. Bayesian persuasion usually focus on the sender's perspective. And this is also what we do in our work for chip talk. But our negative result extends also to maximization of social welfare, where the social welfare is just the sum of the utilities of the sender and the receiver. So now let's briefly see our main results. On the negative side, we prove that there exists a constant C such that it is NP hard to compute a C-sender optimal chip talk equilibrium, both in the additive and in the multiplicative sense, which comes in sharp contrast to Bayesian persuasion, because in Bayesian persuasion, it is well known that one can easily find the optimal sender's strategy via linear programming. And this negative result extends also to welfare maximization. But not everything is lost, because we managed to identify some natural special cases in which we did manage to find a polytime algorithm for the sender optimal chip talk equilibrium. The first such case is when there are constantly many states. The second case is when the receiver has just two actions, which is not that unnatural, because these actions may be, for example, to buy or not to buy some product. And the third case is when the sender's utility is state independent. But regarding this third case, I must mention that it turned out in hindsight that this result was discovered independently before us by another paper using another methodology. And this is the paper by Vohra, Toika, and Vohra. And I must also mention that this paper is the only one we're aware of that studied at least some computational aspect of chip talk before us, despite its main focus was not chip talk. So besides this paper of Vohra, Toika, and Vohra, we are not aware of any more papers that studied computational aspects of chip talk before us. But let's mention some other related work. There are really plenty of papers studying computational aspects of Bayesian persuasion, its various extensions or variations, but not for chip talk. And also there are many papers studying computational complexity of equilibria, but also not in the context of chip talk. Now let's introduce the formal mathematical model for the chip talk game. So we have two strategic players, the sender and the receiver. We also have n states denoted by omega1 to omega n. And the set of states is equipped with some common knowledge power distribution that we denote by P. The true state of nature denoted by omega is drawn from this power distribution P. We also fix some set of possible actions for the receiver denoted by capital A. And we assume that there are m actions, which we denote by A1 to AM. We also fix some set of signals sigma, and we assume that the size of the set of signals is at least as large as the number of states. And the reason for it is that we prove that to implement a sender optimal chip talk equilibrium, n signals are always sufficient. Unfortunately, I don't have time to explain this proof today, but this is what we do in our paper. And also, both agents have utility functions that depend on the state and on the receiver section, and we normalize them to be between 0 and 1. And an interesting remark is that so far the parameters are exactly the same as in the paper by Zugmi and Shu on algorithmic Bayesian persuasion, but still there is a difference from the Bayesian persuasion model, and it is the equilibrium concept. And this is what we're going to discuss in the next slides. What would the equilibrium look like? So first of all, what are the strategies? The strategy of the sender, denoted by pi, is a randomized mapping from the set of states to some set of signals that we fixed. And I remind you that delta of something is just a set of distributions over this set. And the sender strategy, since it maps states to signals, is also called a signaling scheme, as in Bayesian persuasion. And we also denote by S the receiver strategy, which is just a randomized mapping from the signals to the actions. Yes, so upon observing some signal, the receiver is allowed to mix over actions. So let's see the sender-receiver interaction graphically. As I've already said, they both have utility functions that depend both on the state and on the receiver section, and they share the same prior distribution P over the states. So first of all, the sender and the receiver decide their strategies. Then a state is drawn according to the prior distribution and is reported to the sender. Now the sender, given her strategy, the signaling scheme, and the actual state as input, she draws a signal called sigma and transmits it to the receiver. The receiver plugs sigma into her mixed strategy, which maps signals to actions in a randomized way, and draws an action and plays it. And finally, both the players get utilities as the function of the actual state and the receiver's chosen action. And note that when the receiver observes a signal realization, she can update her belief about the distribution of the state to something new, which we call the posterior distribution. And this is done using Bayes' law, and specifically conditional on observing a certain signal sigma, the probability that the actual state is some omega I is the probability that the signal is sent according to the sender strategy conditional of the state being omega I times the prior probability that the state is omega I divided by the unconditional probability that the signal is sent according to the sender strategy. This is just a Bayes' law. And this is the information that the receiver has upon observing the signal realization. And it's called the posterior distribution. So now let's finally define the equilibrium concept. So we're talking about the two-player Bayesian sequential game. And it's really straightforward to compute sender's utility given the strategies of both players. But to compute the receiver's utility, we also need to consider a distribution that the signaling scheme induces over the posterior distributions, because without the posterior distribution, we don't know what would be the receiver's best reply to observing a certain signal. What action should the receiver pick? And what we consider is a special case of a perfect Bayesian equilibrium. And specifically, a chip-talk equilibrium is a pair of a sender strategy pi and the receiver strategy s, such that no player can strictly improve her expected utility via unilateral deviation. But there is a subtle issue here, because one can ask, but what if the sender would like to deviate to a strategy that uses a signal which was not in the support of the original signaling scheme, which means that some signal was used with probability 0 originally, but then the sender would like to deviate to a strategy that uses the signal with strictly positive probability. So why is this problematic? Because in such a case, the receiver will not be able to compute the posterior distribution, and the outcome of the game is totally unclear. But I'm not going to discuss how to formally deal with it. It's actually pretty easy, but let's just say that we disallow the sender to deviate to strategies that use new signals that were not originally used. So a simple example of a chip-talk equilibrium is called Babichenko equilibrium, and it's just obtained from the sender revealing absolutely no information, and the receiver playing any best response. It can be a single action or a mixture of actions. So it's easy to check that when the sender reveals no information and the receiver best response, this is an equilibrium. But of course, it's interesting whether there is something better the sender can do. So let's start from our negative result, which says the following. There is some constant C, which is roughly 1 over 10,000, something like this, but we definitely try to optimize this constant. Standard is NP hard to compute a C-sender optimal chip-talk equilibrium in the additive sense. And since the utilities in this game are normalized to the segment 0, 1, it immediately implies also hardness of approximation in the multiplicative sense. And this result also extends to hardness of approximating the welfare maximizing chip-talk equilibrium up to some additive constant, because we can always scale down the receiver's utilities to make them negligible compared to the sender's utility. But we also have some positive results, and let's just mention 2 of them. So first of all, when the number of states is constant, we prove that there is an algorithmic running time polynomial in the number of actions that outputs a sender-based chip-talk equilibrium. And essentially, it's based on enumerating candidates for the support of the strategies of both players. Another case in which we have a positive result is when the receiver has just 2 actions. So if the receiver has 2 actions, for example, to accept an offer or not to accept an offer, to support the politician or not to support the politician, then there is an algorithm of running time polynomial at number of states that computes a sender-based chip-talk equilibrium. And this equilibrium is very simple because it only uses 2 signals, and moreover, the receiver always uses just a single action as the best response, so the receiver plays a pure strategy. But unfortunately, this proof essentially reduces the standard optimization problem to a single-dimensional one, and therefore it is not generalizable to any higher number of actions, even to 3 actions. So let's summarize. We prove that there is some constant upon which it's hard to approximate a standard-based chip-talk equilibrium, both in the additive and in the multiplicative sense, which is in a sharp contrast to Bayesian persuasion, in which to find the sender-based strategy, it can be done just via a simple linear program. And this result also extends to welfare maximization. And by the way, as for welfare maximization, the only thing we know now is that the problem of welfare maximization belongs to NT. And when we submitted this paper, we didn't know even that. So there's plenty of things to study about welfare maximization. And the computing a Seder optimal chip talk equilibrium is, however, tractable in many special cases, such as when the number of threads is constant, and when there are directions for the receiver, and also when the utility of the Seder is state independent. But I didn't mention it because, as I've already said, it turned out it was proved independently before us, so we're using another methodology. Now we don't know even what happens for a ternary reaction receiver, whether the problem is easy or hard. We have some reason to suggest that it might be actually hard, even for reactions. And there are many interesting follow-up questions beyond what happens for a receiver of reactions or waveform maximization. For example, it's very natural also to ask what happens when we focus on a receiver optimal equilibria. Our main focus on the sender optimal was because our inspiration was Bayesian persuasion. We wanted to study analogous questions for chip talk. But of course, one can also ask what happens when we try to maximize a receiver's incentives. And of course, one can add multiple receivers to the setting and ask what happens there. And also, we have many settings between the two extremities, the Bayesian persuasion with full commitment power of the sender, and the chip talk with low commitment power at all. So in these settings with partial sender's commitment power, it's also interesting to study the computational aspects. Thank you very much for your attention.